Normal distribution. Normal distribution is a very fundamental phenomenon in nature. It also applies for finance and specifically for the stock market. So what is normal distribution? A normal distribution, often called the bell curve, this is a common way to describe how data is spread out or how it's distributed. So it's a symmetrical curve, look like a bell, and it describes many things in nature. For example, if you measure the height of a certain population, or if you measure the IQ of a certain population, you are probably going to find out that the results are going to look something like this. So in the center of this curve, we have the average. So if the average of the results are somewhere here around the center, you can see that most of the density of the result, most of the results are going to be clustered somewhere around the average. So if we look at the example of height, let's say we measured the height of a certain population. So we found out that the average height is 1.8 meter. So we can see that most of the results is going to be 1.9 meter here, and we're going to have 2 meter here, and many results close to that will be always clustered somewhere around the center. But we also going to have some results that far from the center, like this one, 1.5 meter. But as you can see on the curve, we have much less density on the edges, so less likely to have results there. One important aspect about this bell curve is the standard deviation. The standard deviation helps us to understand how spread out the data is. So we can mark these 2 points here, +1 standard deviation, STD, and -1 standard deviation. So the standard deviation tells us how quickly the probability of finding data points decreases as you move away from the center. And if we mark these two points on the bell curve, we can see that 68% of the results are going to be found somewhere around here between these 2 points, plus and -1 standard deviation. But we can also see that between -2 to +2 standard deviations, the yellow lines here, you are going to find 95% of the results. Before we see how to calculate standard deviation, let's see how the stock returns that we learned about in the previous class, how it's related to all of this. So the cool thing about this normal distribution is that it's also applied for finance, or in this case to the stock returns. So if you look at the distribution of the daily returns of a stock, you will see that it looks something like this, or we can say approximately like this, because in real life, this our bell curve is not going to be that beautiful. So if you remember, we looked at the daily returns of SPY, and we found out that the daily returns is on average 0.1%, which means that on an average, the returns, the daily returns of SPY is 0.1%. And if you observe, you will see that most of the returns are going to be somewhere around here, 0.5%, 1% here, and -0.5% here. Most of the results are somewhere around the center, around the average. Or in other words, we can say that most of the results are somewhere around here between -1 standard deviation and +1 standard deviation. And as we have seen before, 68% of the results, in this case the daily returns, will be between these two values, -1 STD and +1 STD. So if somebody asks you, somebody let's say that know nothing about SPY, or you are researching SPY and you want to find out what is most likely going to be the returns today or at any given day. So you can see that most likely the returns are going to be between -1 standard deviation to +1. And let's say you calculated this standard deviation, you found out that it's 1%. So if you found out that the recent standard deviation of a given stock is 1%, you can safely say that most likely, not 100%, but 68% of the time, the daily returns are going to be somewhere between -1% to +1%. And this standard deviation is changing every day, and you have to keep calculating it to get the right results. So let's see what standard deviation is. So the standard deviation essentially measures the volatility of the data, or how much our data deviate from the mean or from its average. So if we sketch here a normal daily returns of a stock, and let's say we are talking about SPY in this case. So the first thing we have to do is to find the average. Let's put the average here, and we are now going to look at each data point, and we are going to find out what is the distance between that data point and the average. So we want to find all the distances from each data point and the average. And essentially what we're going to do is to find the average of those distances, right? So to do that, we're going to put here fake numbers. So let's say that this distance is 10. The distance from this data point to the average is 10, and that's -5, right? And let's say here, this one is -2, this -5, 4, and +4, -4. Okay, so those are not real numbers, but we use them to calculate. So first thing we calculate is the variance. So the variance is the first stage, calculating the standard deviation. And to calculate the variance, we are going to sum the square of those distances. So the square of each distance, +3, 4. So we are going to summarize the square of each distance from the mean. Okay, and once we've done that, we're going to divide this number by the amount of data points that we had here. In this case is 9. So the variance is going to be, in this case, 23.8. That's the variance. So in order to find the standard deviation is just the square of our variance. Okay, the square of the variance. So in this case, this is just the square of 23.8. This gives us 4. This gives us 4.8, and in our case, it's 4.8% because we are measuring the returns in percent. So let's look at how a normal distribution of our stock returns is going to look like. Of course, the reality is not going to be like this, but we will see later. So let's say that the average is here 0.1, and we can say that one standard deviation in this case is 4.8 and -4.8 because we just calculate them. And essentially what it means, as we said before, is that most of our data is going to be clustered around these 2 points. Or in other words, we can say that 68% of the time, the daily returns are going to be between -4.8% and +4.8%. So 68 of the time. Now, we can also print here the two standard deviations, which is 9.6 and -9.6. Those are two standard deviations. And as you remember, we said that in the two standard deviations, we can find 95% of the data. So we can say that 95% of our data points are going to be between two standard deviations, and 68% of the data points are going to be between plus, minus, and one standard deviation. In reality, though, our normal distribution curve is not going to look that perfect. everything we see up until now was a mathematical representation. But in real life, for example, in the stock returns distribution, or even if we measure hate or IQ, as we said, in reality, we're going to get something like this. For example, which means that in this case, you have many more results on the right side of the average than on the left. It's asymmetrical. And in this case, essentially, it means that our stock went up more than it went down. Because we have more density of results on the right side, which is the positive side, than on the left side. So let's see all of this in code. So we import class tree, which is this class. And here on class tree, we have, first we import the API. The API is the module that we programmed in class 1. You can go ahead and check. It allows us to get historical data. Then here we, of course, include pandas and NumPy. Again, if you did not install it, you have to pipe install it. And then we import Seaborn, which will allow us to do all the normal distribution calculations. And here we add two more stuff, the data, datetime, and matplotlib, which help us print stuff, like plot stuff. So we start by defining the period, the dates period, as a string, and then we turn those 2 days to objects because we work with objects here. And then we are creating the data frame with historical data. Of course, we use the function getUnderline that we used in the first two classes. And getUnderline, essentially, it gets the ticker, the first date and second date, and we get the interval and the unit, which is, in this case, a daily data. So then we create a new column called returns, of course, to calculate the returns. So we take the close price and we make the percent change function to get the daily returns. Now we want to calculate this probability density function, which means is the normal distribution. And to do that, we are using something called KDE. KDE is a statistical technique used for estimating the probability density function, which is called PDF. So here we are using it with SNS. SNS, as we just showed, is the Seaborn library that we use, and it have a function called histplot, which will plot the histogram. So we are giving it the values, which is the data frame at returns, the column returns, because we want to find the distribution of the returns. KDE true is, we need this for this function. Bins 60, we use 60 bins to represent data. We'll explain very soon what does it mean. And the color of the line. Okay, so let's go ahead and see how it looks. Okay, so this look not exactly like a bell curve, but as you can see, the straight yellow line show you something close to a bell curve. This is the distribution of the returns of SPY for the last year. And you can see that we have less result on the edges and more result on the center, around zero, around the average. If we zoom in here a little bit to see what's going on inside, you can see here that we divided the area into bins. So each bin in this graph represent a number of returns, and we summarize them to create the bin. So let's explain why we use those bins. So the PDF, the probability density function, let's show how we create the bins that we just talked about. So let's say we have a normal distribution curve, bell curve looks something like this, and say we are talking about daily returns of SPY. So we have the average somewhere here in the center, and let's say 0.1 as we calculated before. So if this is 0.1, most of the results, we actually have infinite number of results on this axis, right? We can have any type of return, 0.15, 0.21, could be 0.28, 0.29, 0.30, etc. So how can we take this infinite number of results and represent them visually to show the density in each area, because we need to define areas, right? So to define areas, we're going to create those bins. We are going to divide the area into those kind of slots or bins. And those bins will all have the same width. And now for each width or for each bin, we are going to check how many returns we found inside that particular area. So for example, the first one, we see 1, 2, 3, 4, 5. Let's say we had 5 return between 0.1 and 0.15. So we have 5. Let's say between 0.15 to 0.21, let's say we have 1, 2, 3 returns here. And let's say between this, we have 2 returns, and etc. And then we do this for, of course, both sides of the bell curve. And once we do that, we get this kind of representation that show us the PDF. And this is the interpolation of it. Like this is a straight line that show the results. So here we use 60 bins. Of course, we could use more, but it wouldn't provide any more information in this case. Let's add the standard deviation to our plot. So to do that, first we will calculate the mean on the returns. So we take the data frame at returns, the column returns, and calculate the mean. And we do the same for the standard deviation. STD is the function that will calculate the standard deviation of this column. Now let's add those values on the plot. So to do that, we use the plot library as always, and we're using a function they have called axvline, which will print vertical line on our curve. So the first one will print the vertical line mean plus standard deviation, right? Because as you remember, we have +1 standard deviation on the right, and we have on the left the mean minus 1 standard deviation. So this is the other line we are going to print. So of course we define the color and the line style. Let's run this and see what happened. So as you can see here, the blue lines, the blue dash lines show you 1 plus standard deviation and 1 minus standard deviation. And then you can see that this curve is definitely not symmetrical. The center is more close to the left than to the right, if I'm not mistaken. But anyway, you can see that these lines, mainly what they tell you is how volatile the returns of this stock are, and those lines can get stretched during time or get more narrow. So let's now see what happens if we check another stock which is more volatile. So let's go to code. Let's change SPY to Tesla, for example, and see what happened when we run this. Okay, so as you can see, the results are scattered around much more wildly, and you have the highest bin is not even on the center of the curve, and you can see that our standard deviation, the blue lines, are much more wider here. That means that the volatility of this stock is much higher, and results can be anywhere between -10 to +10% daily returns, which is a lot. This essentially means that this stock is volatile and is less predictable. Let's try and program some algorithm based on what we learned. In particular, obviously, mean reversion. So let's program some algorithm based on mean reversion. Let's call it mean reversion stupid algorithm. So why stupid, you will understand later. Although this algorithm is very, very popular among people who trade mean reversion. So let's look at a normal curve. As you obviously remember, we said that we can calculate in reality this curve for a particular stock, let's say that according to the returns of that stock, and we get something that obviously not look that beautiful like this, but we get some normal distribution, and we know that 68% of the time the result will be somewhere around the standard deviation, plus minus 1. But we can also assume that if we have one day with minus 5% return, it's way out of the standard deviation area. And we can say that the probability of having that is very low. That means that once we have such results, such return, we can safely, quote unquote, assume that this point is going to go back to normality. It's going to go back to normal, where most of the time our results should be, right? So what if we made some sort of algorithm that says, so when the stock returns are down, are less than some threshold. So let's say this threshold is in 1 standard deviation, or it could be 1.5 standard deviation. Somewhere on the left side under 1 standard deviation, right? We have less chance for this to happen. Say that we buy the stock whenever we have returns lower than this threshold. And let's say that we are going to sell the stock again when it goes up, because we assume it's going to go up, right? Because most of the time the stocks distribute normally around this 68%. So we can say now that when the stock returns are larger than or when they're up, let's say when they're up by 1% or 2% or 0.5%, whatever you decide, we will sell the stock. So what's the problem with this type of algorithm? So to describe it simply, the problem with this algorithm is that we assume that the world is static, which means that the average wouldn't change that much and the standard deviation will not change that much. And if you can see, look at this bell curve here. We have some low returns, but we assume that these returns will go back to normal and we buy it. But what if we have another day of negative returns? The day after, it could happen. What if we have another day of negative returns? Slowly and slowly, what happened here is that our average drifted to the left. And because the average drifted to the left, obviously the standard deviations are new and the whole bell curve is new. And what used to be considered a not normal position, the position where we buy, it's now actually, as you can see, in a totally normal position. It's just a normal position of another bell curve. So we have a new norm. So when we were not in the norm, we expected to become the norm, but now we swifted left and now we are in the norm of a different bell curve. So in other words, we lost. We lost because we are waiting for the stock to go to the norm, but it's already in the norm. It's just a new norm. So let's consider a similar problem, but a bit different. Let's say that the average does not change, and let's say the average stay more or less the same. Another thing that could happen is that the standard deviation will change while the average stays the same. So for example, let's say that the standard deviation will stretch. Now the new bell curve will be wider. That means that our data deviate from the mean much more aggressively. Or on the other side, our standard deviation can shrink, and this bell curve will look like this. It will be smaller. In both cases, we might have a loss. So in other words, we can say that the standard deviation equals the volatility. And volatility is a very popular term, which is very important. It basically says how risky your investment is. So let's get into code. So let's backtest this algorithm on historical data. Let's define a new function that will backtest this algorithm that we just learned on this data frame. The data frame is, as we see in the beginning of the class, is the historical data of this stock for the past year, and we also have the returns column there with the returns of that stock. So let's write this function and go over it and see how we can test our algorithm on historical data. So this is the backtest function, and as you can see, it receives an argument, the data frame. So the first thing we're going to do is to calculate the normal distribution. So we're going to again use the SNS, which is the Seaborn library we used before, and we're going to use the function that's called KDE plot. This will give us the density estimation, which is the distribution of our returns as a continuous variable. So we are going to give this function the returns, right? Because we want to find the returns distribution. Later, once we have that, we are going to ask the x and y axis of this KDE, so we can use them later. So once we have the KDE x and y, which are just lists of data, we're going to find what is the threshold to buy. So as we said, we're looking on the x-axis of our distribution of the returns, where we are in a point where we're not in the norm anymore, right? So in this case, we're going to use NumPy. NP is the NumPy library, remember, and we're going to use a function called percentile. Percentile is a function that can find where, given this list of data XDE, where X% of the data points in this density curve are below that value. Given XDEE, which is the x-axis of our returns distribution, we are going to ask where 30% of the data points in this density curve are below that value, which means we are looking for the point where 70% of the values are higher than that and 30% of the values are lower than that, which means somewhere on the left edge of our return distribution, right? We want the area where we have something that is not normal. So let's go ahead and write the actual algorithm for this buy threshold. Like, we want to buy when we find this threshold and sell later and see if we make money or not, if we did that in the past year. So we define the state because we have a state machine. So it's just a string to define what state we are in the program. And then we define a new column called signal, which will used to mark buy or sell signals. Next, we are going to define a column called profit, where we calculate the profit, and the buy price is just a variable to hold the current buy price. So we're now going to loop over the data frame using the for loop. For IDX is the index, row is each row in data frame. In data frame, iter rows, which is a function that iterate over all the rows of the data frame, and for each row you're going to get the row and its index. So we're going now to iterate over each row, and each row is a day in the year, and we're going to calculate the returns and the price of that day, right? Each row in the data frame have the close price, which is the last price of that day, and the returns. The returns is the column that we calculated before. So as we said, this for loop, every iteration of this for loop could be in one of the two states that we define. We could or be on the first state, which is idle, where we wait for something to happen to buy the stock. And the second state is the wait to sell. After we buy, we are waiting to sell. So now every iteration, we are jumping directly to the idle state. And in these states, we're just waiting for the stock returns to be smaller than our threshold. Remember, we defined by threshold. So we are waiting for the row or the day where the stock returns are smaller than this threshold. Once it happens, it means that we buy. So buy essentially just means that we change the state of this state machine to wait to buy, to wait to sell. And then we mark the data frame on that row, this index. So we're doing data frame at index in signal. Signal is the column where we mark buy or sell, and we mark it as buy. So this column on this row will have the word buy. You'll see later how it looks. And we save the price that we pay to buy that stock. Now, because now we bought it, we change our state in the state machine to wait sell. So now each iteration of this for loop, we're going to jump right into the state of wait sell, right? Because this is the second state. So in this state, we essentially wait for one of the two to happen. We're going to sell or if we make a profit or if we have a loss. So we're asking when is the price of the stock is larger than 1.01% of the buy price, which means is 1%. So whenever the price of the stock is higher in 1% from the price that we paid to buy the stock, or it's smaller than 0.98% of the price we pay to buy the stock, which means the stock fall 2%. In either case, we want to sell, right? We have a loss protection here of 2%, and if we make 1%, we also take the profit. If that happens, we change the state to idle because we want to mark our state machine to go back to normal and wait for the next round, and we mark the signal column like before as sell, right, on this particular index, on this row. But in this case, we also mark the profit. The profit in that index equals the price of that day minus the price we pay to buy the stock, right? Because the buy price is the price we marked before that we pay to buy the stock. Okay, so now when we have the profit column, the profit column which mark for each position, for each deal, we see the profit. We have the profit, which could be negative or positive. Once we finish this for loop, first we calculate the total profit, which is the data frame at profit sum, right? Take the profit column and summarize all the positions, the profit from all the positions. And the next thing we want to do is to calculate the win ratio, which is how many times we win divided by the total positions. So we are doing data frame at profit larger than 0, which means take all from the profit column, take all the cases, all the events where we have positive returns and summarize them and divide this by the total amount of deals, which means every time our profit, which was 0 in the beginning, every time our profit was not 0, which means every time we have any type of, we took any type of position. So, and we summarize it. So essentially the win ratio telling us how many times we win in percentage. So the next thing we are doing here is just to print those results. So we're going to first print the returns threshold. Remember that we calculated by threshold. We want to see how much is it, right? And second thing, we are going to print the date, close, returns, and signal and profit columns of the data frame. And we are going to print the profit, the total profit, and the win ratio that we just calculated. Let's run this and see what happened. So we run this and let's see the results. Okay, so first we see that the returns threshold is minus 0.3, which means that's the point where we want to buy, right? This is the not normal point in our distribution that we decide that we're going to buy. So each line here is just a day with of the stock, with the close price, the returns, etc. So let's look at the first deal, the first time we buy. So you can see in the signal column here, buy. So we bought the stock because the returns were -1, and -1% is lower than -0.3, which means that we crossed our signal, so we buy, and the price that we buy is 373.2 USD. So let's see where we sell. So we sell it right here after, and when we sell, the price is 362.79, which means there was a big loss. There was a big loss, and our algorithm say if there is 2% loss, sell. So here you can see we lost $10. Let's look at the next deal. We bought it here where the returns were -0.76, and the stock price was 360. So in this time we bought it in 360, and a few days goes by and price change, and then we have sell signal. Why? Because if we look at the stock price in this date, price goes up by more than 1%, 365.97. So we had a profit here. The profit in this case was 5.95. So you can go over all the results like this, and you can see that for each position we took, we have or negative or positive results, etc. So if you go over all the year, which this is what our for loop did, you can at the end get all the positions profits. And at the bottom line, you can see we print the total profit, which is 94.3 US dollar. In this case, we assume that we buy one stock at a time. You could buy 100 or whatever you want, but so this should be multiplied by the number of stock that we bought, and we see that the win ratio is 0.77, which means 77% win, which is not bad. But as we said, there are many problems with this algorithm. So let's check what would happen if we run this algorithm on a stock that is much more volatile. For example, Tesla. What happened? What would be the profit and the win ratio? So let's go back to the program and put here Tesla instead of SPY. Let's run this again and see what happens. So the first thing you can see that the returns threshold, the threshold to buy the stock in this case is -5.26, which is way lower than the SPY one, which was 0.3, -0.3. And why? It's because Tesla is a more volatile stock. You need a much more aggressive move in order to buy. So let's look at the first signal. We bought it here because we had -6.3 returns, lower than threshold, and the price we bought is 223 USD. And 2 days later, the stock went down to 216.5, so we had a loss, and we sold for a loss for -6. We lost -6. So you can go over this table and you can see all the deals, buy, sell, and you can see positive or negative profits. And if we go down to the bottom line here to compare, we can see that the total profit here is 37, which is almost like a third from the SPY total profit. And the win rate here is 0.68, which is also a bit lower than the SPY results. Going back to the name of this algorithm, we called it the stupid mean reversion algorithm. So why stupid? As we showed in the sketchboard, we assumed here a static world. We took a year of data and we calculated the standard deviation and the mean for the full year. But as we said, those things change on a daily basis. So in order to solve this, we are going to use moving average and a few other tools. We will see this in the next class.